Test now. Yes. There you go. Boom. Sound fixed. I should have noticed. I'm such a noob. Okay, I think I fixed the sound now because I can see that in OBS. Let's wait a second. Yes, sound is coming through. Yes. Cool, perfect. Sound is coming through. So I'm gonna start over. I'm gonna repeat what I was saying before. Give me a second, guys. Okay, perfect. So what I was saying is that by no means. So first of all, 2 points that I want to clarify is that and I'll do quickly because I'll do this quickly because I only have barely an hour. So essentially, so for those who haven't seen and watched any of my streaming before, I am basically, so I'm not prepared for this kind of stuff, right? I on purpose, by design, do not prepare the streams, do not prepare what I want to say, what I want to touch, what I want to play with. The reason being that I want to give my most genuine experience with the stuff that I touch. So just to clear things off, I am basically, from a background perspective, I studied computer science a while ago, a long time ago actually. So I do have the basics. I'm not a programmer in my day-to-day job because I think programming is something that I basically want to do out of passion, not out of like being paid a paycheck for. But that's a different story, not for now, not for today. Anyway, so the point being here as well is that I'm not affiliated with Extropic at all. So just to say, to leave that clear from the start, I've known Guillaume for a while because I got to know him via X when I started my YouTube channel on quantum computing in 2019. That's a channel that I don't really post much to anymore because I do a lot of the stuff now just directly on X. But yeah, basically, I think Extropic is a crazy interesting concept, and I'm just attracted to the stuff that I'm naturally attracted to the stuff that I feel I don't fully understand. And that's why we're here today. We want to play with whatever we can, and I'm probably going to do more of these because now that Extropic has released a bunch of stuff yesterday, there's just a lot to go through, and I'm not going to go through hardware. I do not have access to any of these, and I won't waste time now reading the articles, although we might have to go to these. And again, as I said, I'll just go through these. What I wanted to take a look is I want to take a look at the THRML, which I guess is for thermal. But I guess it's, with ML as in machine learning in here as well to play the nice war game. Is a library to construct thermodynamic hypergraphical models, a fabric of probabilistic models made to be run efficiently on TSUs. First things first, I am going to be using Grok a lot because I think that's the best and most efficient way to explore these kind of things. So let's see whether we can make the sense out of these. Again, as I said, I haven't prepared. I just want to see if I can do something with these. I can touch something. I can understand a bit more what this is, and maybe maybe we get to do something. But yeah, basically that's it. So I think, so first of all, there is a library and examples available on GitHub, which is awesome actually. And we're probably going to be spending a lot of time here today. What I should probably do, yeah, okay. So, I'm just paranoid. I just hope that the stream is going through. I'm just paranoid, guys. Yes, live. Yeah, okay, perfect. Cool. So first of all, let's just read through these quickly. Thermodynamic hypergraphical models. Let's just ask Grok what that is. thermodynamic hypergraphical models. So that's for sure one thing to ask. Then we have here algorithm development, simulate TSUs, use JAX. JAX is like a framework like not Google. JAX is like PyTorch and stuff, right? I think it's a Python library developed by Google. Okay, yeah, okay. An NumPy-like interface to run stuff on CPUs, GPUs, TPUs. TPUs are tensor power units, right? I think. I think these are tensor. I think the T stands for tensor processing units. Yeah, exactly. Because that's the stuff that is. I think that's the one. Those are the ones that are developed by Google, right? Custom designed. Developed by Google, yes. Okay, all right. So it uses JAX to massively accelerate simulations of PGMs. What are PGMs? So we'll go and first, so THMs are a specialized class of probabilistic graphical models that integrate principles from statistical mechanics and thermodynamics to represent complex energy-based probabilistic systems. They extend traditional graphical models by using hypergraphs structures where edges, called hyperedges, can connect multiple nodes simultaneously. Funny enough, I did stuff with hypergraphs when I was doing entanglement, because I think quantum entanglement is something you can represent with hypergraphs very neatly. Can connect multiple nodes simultaneously to capture higher order interactions among variables, making them suitable for modeling intricate dependencies and data, such as machine learning. Okay, so those are basically physics simulations, biological energy-based framework, probability distributions as arising from an energy function inspired by thermodynamic systems. The energy of guys, like most of the stuff that I'm reading, I don't fully understand, right? So just that's the way that I go about things. I just kind of read through and then drill down. Is the energy of configuration X and T and temperature parameter controlling exponential sampling. Okay, so how do they work? You define a global energy function as a sum of local factors over hyperedges. I guess what you're doing, so you have nodes which represent your variables. And then you have the hyperedges that represent how they influence each other or how they are like related to each other. That's kind of what I'm guessing out of these. And as a model of Ryan, spins interact via hyperedges representing multi-body potentials. Well, that is, I mean, it's cool because that is really, when I said, and I have, you probably can look them up. I have a couple of videos on me trying to construct a hypergraph interface to model quantum entanglement, and it's this, right? Because you have the nodes being the qubits and then the hyperedges being the way that the qubits are entangled, right? Or the entanglement between qubits. So designed for energy efficient probabilistic computing in AI where traditional neural networks are power hungry. So energy efficient probabilistic computing. I need to dig into this. What's my best next question to ask, Rock? Treat probability distributions as arising from an energy function inspired by thermodynamic systems. Is this then just a way to define a probabilistic distribution? I guess. Give me a THM example. Simple THM example. I might switch to voice mode because actually I think voice does quite well at simplifying things. All right, so we have simulate. So, okay, so you can simulate TSUs of PGMs. I still don't know what PGMs are. What are PGMs in this context? What are PGMs in the context of this text? Cool. And then we have how to design machine learning train energy-based models. Then we can compute gradients. Okay, that's actually interesting. So it can compute gradients in probabilistic graphical models. Oh, that's what PGMs are. Probabilistic graphical models. That's probably what I'm interested in so far. I think a bit more to explore. Maybe because I feel a bit more confident that I know something about these, even if it's just a little bit. Probabilistic graphical models. These are the class of statistical models that use graph structures to represent and reason about the joint probability distributions over multiple random variables. Haha, it already knows about THRML. Cool. Oh, well, I just put it in here. I guess. No, but it probably found it on the web. Yeah, Extropic AI. Okay. Okay, it doesn't know, but it just found it. Okay. And I was rapid prototyping and testing these models. Give me a simple PGM example. And by the way, you're going to be hearing a lot of baby crying in the background, I'm assuming, because I don't have sound filtering properly set up, but it's fine. That's what it is. So, simple THM example, 3-spin hypergraph model. A thermodynamic hypergraphical model can be as simple as an energy-based system over a small hypergraph. Here we'll model a 3-node hypergraph where all 3 nodes are connected by a single hyperedge representing a 3-body interaction. The energy function, whatever that is. So Fabus configuration is where the product S1, S2, S3 is equals +1. Again, for context, I'm reading through these. It doesn't mean I understand what these things mean. Okay, so I need to figure things out. That's why it's going to take a long time, and we're not going to really go very far in 1 hour. That's all I have today. But we'll try to do a bit of a stream every day if possible. We'll use Gibbs sampling to generate samples. Based on the Metropolitan criterion, whatever that is. This is implemented in plain NumPy. Okay, so actually there's something here in plain NumPy. Simple. Okay, so we're defining a model. This model has, I mean, we're still in abstract realm. I want to try to find. So your sampling states, basically. I mean, can we just try that? That's just like NumPy, right? Okay, so sample states, first 10 states. Sample run. Sample. Low energy states. Let's start a thread. What was the thread one? Start a thread. So this simple example. What is the simplest, more tangible thing I can relate it to? That helps me always, because this is all pretty abstract. And that's what makes it hard to get into, right? Let's go back here. We were here talking about PGMs. Bayesian network for rain and sprinklers. Okay. So probabilistic graphical models are a way to present complex probability relationships between variables using a graph. Nodes represent random variables, events or measurements, and edges represent dependencies. This makes it easy to compute things like the probability of an event given others. Yeah, exactly. A common type is a Bayesian network. The grass is wet. I mean, I like that example, actually. Okay. Imagine a simple scenario where we're trying to figure out if the grass in your yard is wet based on whether it rained or the sprinkle was on. The variables are Rain, did it rain or not? Sprinkler, was it on or not? And wet grass, yes, not. Okay, then dependencies. Okay. Yes. Makes sense. Assign probabilities. These forms are directed at a cyclic graph. HRS, rain affects sprinkler usage. SW, sprinkler affects wetness. And RW, rain affects wetness. Yes. Assign probabilities. We define the conditional probability tables. Chance of rain, blah, blah. I mean, that's a simple example, yeah? Computing an inference. Suppose we observe the grass is wet. What's the probability it rained? Using Bayes' rule and the graph structure via algorithms like variable elimination or belief propagation in PGMs, we can compute the joint probability, marginalize over S, and then normalize. After crunching the numbers, 20% chance it rained, given wet grass, higher than 20%. Sprinkles make rain less. Okay, this is the example. Yes, I like it. So there is actually tools like Python's PGM PI can implement these easily. All right. I mean, we could maybe go down this avenue because that's very, very that's very practical. It's a yeah. Sorry, Extropic. I don't mean to use your software to model rain and sprinklers. Can compute gradients in probabilistic graphical models, which can be used to train energy-based models. Okay, but that's probably not what this is going. Wait a second. What did it tell me here? So tangible analogy, a 3-switch light system. The 3SP model is abstract, but picture it as a 3-light switch controlling a single quirky lamp in your living room. Each switch can be up or down. The lamp works best, low energy, happy state, bright and efficient, only when an even number of switches are down. All up, lamp blazes happily. 0 down. Exactly 2 down, lamp glows warmly. 1 down or all down, lamp flickers annoyingly. Okay. At room temperature, the switches flip randomly, exploring all combos, but crank the AC. What sells it to those? Your Gibbs sampling is just the switches randomly testing flips until the lamp chills out. This mirrors real multi-way switch wiring common in hallways, but with a fun even rule twist, like the house elves prefer symmetry. What the fuck? Way more relatable than speed. Yes, awesome. Grab 3 actual switches and a bulb to demo. Want a diagram or a code to simulate the lamp brightness? What? But wait a second. I'm kind of getting lost here. So okay, so you're telling me that this is something where, so you'd model these, you'd build these example of a THM, and then you would model and expect that you're only sampling minimal energy stages, states, I guess. Okay, let's go take one step back. So on one side we have PGM simulation. How did I get into the THM stuff in the first place? Thermodynamic hypergraphical models. Here, so I have to construct, okay, so you construct thermodynamical hypergraphical models. Okay, but that's because they are related, right? I guess that's the THM is something that can be used to implement a PGM. I think that's what this means, right? A side question. How are THMs and PGMs related? I assume the relation is that THM can be used to implement a PGM. right? I guess that's what it means. These are advanced class of probabilistic models, structured as hypergraphs, exactly. Okay, THM is more of a concept, so it's more of the term that is actually then related to the fact that it's designed to harness noise in hardware. That's how the air chip is actually built. Because the idea is, I think the whole idea of Extropic is that you're modeling the noise distribution on the chip. That's what I understood back then. That's what this is supposed to do. That's what their X0 is supposed to do. Wait. Yeah. So essentially, that's basically. Oh no, they announced XTR0. And a traditional processor. Okay. So essentially, they've designed a way to. So essentially that is basically this one that can interface with like an actual chip. Okay. Because I think that's the whole point of these, right? Oh, TSUs are thermodynamic sampling units. So these are not the tensor things from Google. I know oh god, fuck, these are TPUs. I'm so stupid. Probabilistic circuits. Yeah. So I think that's exactly. So we're yeah, I feel we're kind of peeling that off a little bit. So let's see. So essentially, THM is a term that refers to what you can implement on the chip, and PGM is the more abstract. Is the foundational framework, the graphs that encode joint probability distributions. THMs build directly on PGMs by extending them into the thermodynamic domain. Okay, exactly. Okay, so the PGM is the theoretical, like sort of the foundation. THM is what is then adding thermodynamic. Yeah, okay. THM adds this energy thing, the energy function, I think, right? Is a specialized class of PGMs. Okay, yep. You see, it takes time sometimes to figure these things out, guys. Connect the dots. So we've got PGM as the basis, theoretical basis, which is encoding probabilistic models using graphs or hypergraphs. Then you have THMs, which it's a specialized case, or it builds on top of it, which basically what it does is it extends. Okay, now it kind of makes sense. It extends traditional graphical models by using hypergraphs. Okay, no, so THM is what uses then the hypergraphs. Yeah, that's why here when I'm looking at that, it's not using a hypergraph. It's just using a normal directed graph, directed acyclic graph, right? And so THM says no, it's a special case where we're using hypergraphs only, and to capture. Is that the only special thing about THMs? Treat probability distributions as arising from an energy function. Exactly. It's private thermodynamic systems. The probability of a state is. Okay, interesting. So the probability of a state is proportional to these. Add to the chat. So where E of X is the energy of a configuration X, and T is the temperature parameter controlling exploration during sampling. The hypergraphical aspect refers to the use of hypergraphs to define factors, local energy terms, that influence groups of variables. Factors. Okay, so I guess those factors then. Okay, so what we have is the THMs. So THMs introduce the following: hypergraph usage for the PGM model, probability definition constraints, proportional to these. We're learning, okay, guys? We're learning. So, proportional to these. What else? I'm trying to kind of peel off that concept first, right? I'm trying to understand, okay, so so we're going from a definition of a PGM, and we need to understand what a THM is. And so that's why I'm kind of trying to understand, okay, so if it's a specialized case, then it means it adds constraints to that. And so let's first understand that. Innovations. Oh. Building on the hypergraphical structure for probabilistic graphical models. I need to check what that is. Constraints for probability definitions introduce several other key advancements. Primary focus on efficient inference, hardware integration, and scalable. So block, Gibbs sampling for parallel inference. Okay, but that's more of a hardware thing. Hardware native execution, that's fine. Chaining of, because this is all taken from Extropic, right? So chaining of energy-based models. Is THM something that Extropic has coined? Who coined the term THM? That's not what I was looking for. That's not the answer I'm looking for. I'm looking for at a theoretical level. So thread. I'm looking. What constraints do THMs add to PGMs that make them a specialized case? Can it run a thread? And yeah, it can run that in parallel. That's cool. So, okay, so they coined the term. That's an important thing. Okay, that's cool. So Extropic actually coined the term. Okay, cool. These constraints collectively position THMs as thermodynamically constrained, subset of undirected. Guillaume's background. And Trevor. Okay, so while no single individual is explicit credit announcement, the document aligns with the company's research led by feels like okay. Really, did they really coin it? X posts, whatever. No. Okay, those are just announcements from the staff from yesterday. Fine. And here, okay, so here we have sparse module locality, homogeneous temperature scaling. Hypergraph topology, we got that. Okay, that's too complex for now. I think I can't make that jump yet. Let's step back for a second. But we know that THMs is a specialized case of PGMs. That's good. Cool. and here we had a PGM, and then can we model the same example? THM. Is a fundamental concept in statistical mechanics, but this is how energy is shared among particles, and states it tells the probability that a system will be found in a particular energy state. Okay. So probability of being in state of energy E, K is Boltzmann constant, tiny number, like energy and temperature. Okay. Low energy states are much more probable. Okay, yeah. So it's basically basically probability distribution for energy. Okay, so what has Grok done here? Pseudocode. That's pseudocode in thermal. Okay. 3 binary spin nodes, factor edges, parameters derived from CPDs, bias weights from log probabilities, use block use for posteriors. Okay. No freaking idea. What is the best way to move forward? I want to pick an example. I mean, let's take a look at the repository. So we have here that thermal is a Jackson for building and sampling probabilistic graphical models with a focus on, okay, but here is telling me that it's not just THMs, right? So it could also just build and sample a generic probabilistic graphical model. With a focus on efficient block Gibbs sampling and energy-based models. Extropic is developing hardware to make sampling from certain classes of discrete PGMs massively more energy efficient, provides GPU accelerated tools for block. Okay, so what this is a library that allows you to model PGMs, and then it comes with functionality that simulates their chip using GPUs. I think that's probably what this is. So we don't know what block Gibbs sampling is. We don't know what pi tree node states are. We don't know what heterogeneous graphical models are. Discrete IBM utilities enables experimentation with future extropic hardware. From a technical point of view, the internal structure compiles factor-based interactions to a compact global state representation, minimizing Python loops and maximizing array level. So here's the documentation. Cool. Oh, perfect. I think we can spend some time in here. Examples. API reference. So thermal.ai. Do they actually have a web? No. Like, did they? Okay, no. There's no upper. Okay, that's just the GitHub's. Oh no, this is the repo. They don't have. I think that's actually a GitHub page, isn't it? I don't know, made with material for MK docs. Okay, just the doc side. Okay, all good. Sampling a small Ising chain with 2 color block Gibbs. Okay, so here you define the nodes, you define the ages, you define the biases. Okay, so that's all. I mean, this is, I guess this is just the hypergraph definition. Then they seem to have like a specific class for the Ising model. And then you make a program, a sampling program. Jack's random key. Like initialization, and then you're doing a sampling schedule, and then essentially print the samples. So I mean, I think high level is easy to understand. You're defining your model, you're defining your sampling schedule, the way you want to sample, and then get the samples, right? So it's Jack's. What I'm not sure is how that runs on a GPU then. So installation and quick example. Can we try this? Let's just try this. What I'm gonna try is I'm gonna try to use grok fast and cursor. So I'm gonna try to do these. I'm gonna try to open cursor. And I'm gonna try to actually, let's make a project. So let's go, whatever agent thing I had. Let's make a thermal folder. And then let's just open thermal. Let's just kind of stay here. And then let's ask it, can you pip install thermal? Yes, I'm that lazy. I'm using grok code fast, yes, cool. And then we'll ask it to run this example. Sampling a small icing chain with 2 color blocks. Do I just copy and it's like, can you, at this point, this way of using a model is actually funny. What's going on? Is the from a different source like GitHub? Yeah, but it should be actually pip install thermal. Should work actually, right? Is my setup like so fucked up? Did it try just pip install thermal? Pip. Can I not just like spip? Well, how am I supposed to? How is it supposed to? How install pip? I'm not even. I have no idea how is this machine set up. Pip is working. Awesome. Now try. No. Thermal. Yeah, but it still says pip. Okay, pip3. Later, pip3. Install. Ignore the following versions that are a different Python version. What Python does it require? What version of Python do I have? It requires 3.10, I think I saw. Installation. Is my setup that fucked up that I can't even set this up? Okay, no, it's actually installing something. Because I think I have Python 3.9. I don't want to install it from the repo. I think I want to see if it's kind of like working from whatever is available there. If not, we'll do that. That's all good. That's all good. Okay, now using 3.10. Let's use 3.10 and install THRML. Oh, I actually have to run it. I cannot. What is it doing? Why am I having some problems with the directory? Okay, it's not loading it. I think it's not loading it, guys. Well, it's not loading jacks, not loading thermal. Oh boy, I'm so happy that LLMs exist. Like I like. Okay, successful install. This is the useless shit that you don't really need to know. And it's where you lose most of the time. I would have lost the entire fucking hour for this. Success. Okay, cool. Okay, let's try to do this now. Let's ask it. Okay, so I wanna. So they give. So Extropic has this example for thermal. Can you please build it and run it? Yeah, let's close the. Yeah. And I should upgrade cursor to the new version 2.0. MS Python for the Python language. What is that? Fuck. Okay. Okay. So okay. Cool. Okay, actually it worked. Look at this. It actually ran it. Okay. It seems like it ran it. Sample 0. Whatever that is. Okay, but we have now. Okay, so we have it. We installed it. We have the example running. So success, as the model example is working perfectly, sampling completed successfully, 1,000 spin configuration sample from a 5 spinizing chain, 100 warm-up steps. Run it again and type the results into a text output file. And I think it has voice mode cursor too, right, as well. So we can do these. That's cool. But okay, that's simple. So we've installed that. We're running with these. 10 configurations, spin statistics, acceptance rate, blah blah. Okay, but it actually, okay, so it works. I guess we definitely want to get into these then. We definitely want to read these through. So it has a problem, an example problem, I guess, a concrete example. What probably is the computer? Okay, so let's start here. Extropic hardware will become increasingly capable over the next few years. Probably just gonna increase the size of these. Okay, given these short time, simulation library is a GPU simulator of the probabilistic sampling programs that run natively on Extropic hardware. It's built on top of JAX and is massively scalable. Okay, cool. So you can simulate large probabilistic computing systems. It's a simulation library. Cool. So what's a probabilistic computer? Probabilistic computers leverage arrays of massively parallel random number generators to sample from distributions that are relevant to solving practical problems by leveraging physical effects to generate random numbers and emphasizing local communication. Probabilistic computers can process information extremely efficiently. These sampling-centric computers make direct contact with contemporary machine learning via energy-based models. Much like popular diffusion models and others, APMs attempt to learn the probability distribution that underlies some observation of the world. You need to try to directly learn the shape of the distribution instead of attempting to represent it via composition of many size simpler distributions. Probabilistic computers, yes. Particular symmetries of certain families of EBMs can be leveraged to map EBM sampling problems directly onto probabilistic computing hardware. And there's a paper. Okay, how do computers work? To truly understand how exotic computers operate and their utility in ML, we must examine the underlying mathematics of EBMs and the algorithm that enable sample from them. Okay. So the EBMs attempt to model data distributions by learning a parameterized energy function in which defines the shape of a distribution. Here X is a vector of random variables that represents the data that you want to model, which could be text, images. EBMs are fed by tweaking the model's parameters to assign low values of energy to values of X that show up in the data set and large, yeah, exactly. So essentially you're modulating, you're creating that probability distribution by just assigning energy values. Both inference for EBMs, both inference and training involve sampling from this potential very complex problem. That's what I was going to say. I think the difference here between this and the current model, the current way of training stuff is that you're training them by sampling, right? Or not? Is that how do you calculate the how do you do gradient? How do you train here? On the GPU's review at inference time, we aim to generate new data that resembles data set. There's a lot to digest here, guys. As I said, I'm very new to these, so it's if a probabilistic computer can make this sampling very efficient, yes, that's clear. Factorized EVMs. They are embodied by a circuitry that lives in nearby parts of the chip. Probabilistic computers leverage the keep sampling algorithm to efficiently sample from these special EBMs. A concrete example. Let's take a look at a more concrete example. Here we'll implement a simulation of a simple probabilistic computer sampling from an EBM using THRML. We'll implement sampling for a POTS model, which is a type of EBM that was first developed to study various phenomena like solid-state physics. POTS models have energy functions like these. A POTS model. What is a POTS model? Phase transitions and behavior interactive systems with magnets or alloys. What was I here? yeah, I mean, whatever the example is, right? You have an energy function, use thermal to run block Gibbs sampling on a POTS model. For first, some importance that will be useful. Block Gibbs spec. The POTS model energy function naturally suggests a graphical representation. Namely, we can assign each random variable in the problem to a node and assign biases to each node to implement W. We can connect variables with edges to represent the interactions. This is actually pretty neat. I mean, it's basic grid, although it's capable of dealing with arbitrary graph topologies. Grid graph convenience. Color groups for later. Down the edges in a different format for later. Plot the graph. The graph we just drew can be interpreted as a high-level schematic for a probabilistic computer. I thought that was supposed to be your problem that you're encoding. Which could represent physical wires. Ah, okay, I know what you mean. You mean that that's exactly how you've designed the chip has natively this type of structure. You have nodes that are connected with other nodes, and that's why you're essentially when you model your problems like these, then the chip does exactly that, I guess. Comes with a canned implementation of POTS model that we can leverage here. Consider simple cases commonly studied in physics with no biases. Okay, so there's already a POTS model in the library. Cool. I think what I will do. And I have to make another stream where I actually build a problem. I code one from scratch using that. Essentially, why don't we? I'm trying to see what is the next useful thing that we can do that it helps me understand a bit better how this works. An EVM. What can I do with thermal? I mean, here it just seems like all I'm seeing here so far, it's ready built models, really? Could it be POTS models? So, but what I want to do is I want to maybe see if I can use a GPU or something, rent one, and actually train something. Graphical model components, block management. I don't know what blocks are, interaction groups, factors. We're going to learn the shit out of these guys. We're actually going to do these energy-based models, discrete energy-based models, Ising models. How do I train? So I mean, that's the first question is, can I train a model using thermal myself on some GPUs? I don't know if the stream is gonna shut down automatically in 3 minutes because I think I set it to 1 hour. But yeah, so it's does support training models. Yes, you can train models in thermal on your own GPU as an open source checks designed with energy-based models. The noising. Okay. All right. Enables training of discrete EVMs, Ising models. Okay. Installation setup, train EVM. Okay, we'll do that in the next stage. Train step. We'll train an EVM. We'll do that, and we're gonna do. What was that? What was the company called? No, what are these guys called? I forgot. I'm gonna find them. There's this other lab that does also GPU renting. I found them on. What was this? Something with intellect. I found them on X the other day. I'm so bad at names. Rent GPUs. Fuck. I'm gonna find them. I forgot what I forgot their name. I forgot their name. I'm gonna find them because I always wanted to use them and I forgot that. Anyway, guys, I'm gonna drop it here. What we'll do next is we're gonna train the we're gonna dive straight into like training a these. We're gonna go straight into training a discrete EVM. Okay. We'll start here next time. All right, that was definitely a fun hour. I think I've definitely gained a solid basis, or at least I've kind of carved a bit of knowledge out of all these. Cool. See you in the next session.